Hello, everyone. Thank you for inviting. I'm happy to be here. And today I will talk about K-stability of family 3.5 in Mori-Mukai classification. So, first of all, what do we know? We know that a smooth Fano variety X admits a color it's diametric if and only if it is K-polystable. For dimension 1, we know that projective line is K-polystable. For dimension 2, we have Pezzo surfaces, and they are K-polystable if and only if it is not a blow-up of P2 in 1 or 2 points. And for dimension 3, they were classified as smooth Fano threefolds were classified into 105 families. And in a large book, the following problem was posed. It was find all K-polystable smooth Fano threefolds in each family. Today we're going to talk about δ-invariant. So we define it as the infimum of AX of F over SX of F, or where AX of F is log discrepancy and SX of F is the integral, which we will define later on. Just this slide is for the introduction of this invariant. So we have some invariant which will later on help us to define if something is K-stable or not K-stable. So the following assertions hold. X is K-stable if this invariant is greater than 1, and X is K-semistable if it's greater or equal than 1. And similar, we can define for the threefold X the local δ-invariant, so it's log discrepancy over this S integral, which we'll define later on. So if it's this local δ-invariant is greater than 1 for all points in this threefold, then X is K-stable, and if it's greater or equal than 1, then it's K-semistable. We also have a bonus round theory, which helps us to understand if something is K-stable or not K-stable. So suppose we have a point in a threefold X, and we want to estimate this δ-invariant. The first thing we do, we choose a surface S such that it contains this point. Then we compute the pseudo-effective threshold, the big threshold of this divisor. So we have the anti-canonical divisor on this threefold X. We have this surface, which we chose earlier, and we find the number for which this divisor is big. Then on this interval, which starts with 0 and this ends with this tau, we compute a positive and negative Zariski decomposition of this divisor. And then we compute this S invariant, which I mentioned earlier. And after that, we can estimate our local δ-invariant from below as the minimum of 1 over this S and a filtration and the delta filtration, which is defined as our log discrepancy over all prime divisors over the surface S over this SV integral, as we will refer to it later on. So it's a large integral which can be computed explicitly after we know the Zariski decomposition of the initial divisor, our surface S, and that's basically it. I know that it looks a bit scary, but what we need to understand from this, that at the end we need to know 3 numbers. We need to know our log discrepancy, A, this S integral, and this SV integral, and it's all of it is countable. So after knowing the Zariski decomposition, all of these numbers can be computed, and the estimation for delta, a local delta, can be found. And after we know the estimation for local delta, we can understand if we can estimate if its local delta is greater than 1 for all points or not. So what we do, we take the point, then we take the surface which contains this point. Then we compute the risky decomposition for the divisor minus kx minus us. And for smooth finite threefolds, it exists. Then we compute these three numbers. So we compute the log discrepancy, then S integral, then SW integral, and then we do our estimation. And if we are lucky and it's greater than 1 for all points, then X is K-stable. But this can be, in all of these computations for threefolds are quite scary, and they look better on surfaces. So let's look how we can look for it on surfaces. So suppose we have a smooth surface and a big enough divisor on this surface. Then for every prime divisor over this surface, we can define similar kind of S invariant as we did before. So here we have 1 over our big enough divisor on S. And here we have the volume of divisor D minus VF for every prime divisor F over S. To compute the volume, we need to compute the positive and negative part of the Zariski decomposition of this divisor. Similarly, as before, we can define a local delta invariant for this pair SD. So the local delta invariant for the pair SD, where S is the surface and D is a big enough divisor, can be defined as the ratio of the log discrepancy over this S integral, where the infimum will be taken over all the prime divisors over the surface S, whose center will contain our point P. And usually, if our divisor is just the anticanonical divisor, then we drop the D and just denote it by delta P of S. Now we are interested how to estimate it. From above, it's done as follows. So first we fix a smooth curve which passes through P. So remember, now we are just on the surface. We have a point P. We have this surface. Then we want to choose some obvious or not so obvious curve C, which will give us our estimation. Similar as before, we compute the pseudo-effective threshold of the divisor D minus VC. So it is just the divisor on the surface. So all the computations will be easier than before. Then on this interval, we compute the positive and negative part of the risky decomposition of the divisor D minus VC. Then, since this curve C belongs to our surface, then the log discrepancy is just 1. And we also can compute our S integral. Then we have that our local delta invariant is less or equal than 1 over our S integral. Why is that? Because our local delta invariant was the infimum of this thing. So here we have just log discrepancy 1, and here it's one of the S integrals, because our F in this case is the curve C, which belongs to the surface S. So this estimation we get directly from the definition. We are also interested how to estimate our local delta from below. We get this estimation from Abundant theory, which was mentioned earlier. So we compute this long SW integral, which is defined similar as before. So only here we'll have 2 over our divisor d, which was defined earlier, and we only need to know the negative and positive part of the risky decomposition. Here we just get the intersection of curves, so all the numbers can be deduced way more easily than we could do it on threefolds. On threefolds, it's not obvious how to do this, but here we just have the intersections of curves, and if we know the structure of the surface S, which was mentioned earlier, we can just see all the intersections and understand all the computations. So, and this sum can be rewritten as 2 over d squared. Sorry about that. 2 over d squared and the integral from 0 to tau, where our tau was the pseudo-effective threshold, and the integral from this function. So usually it just a simple polynomial, which we can easily integrate and get our result. Not always, but usually it is. Then it follows from Abundant theory that this local delta is greater or equal than minimum of these two inputs. So this is 1 over S integral, which we calculated earlier, and this is 1 over S W integral, which we calculated now. And from not always, but usually for negative curves C. So if our point belongs to some negative curve, this gives good enough estimation to know the exact number for local delta invariant. But sometimes there is no such curve C, negative curve C, which contains a point P. So we are interested how to estimate this local delta, and we're still interested how to estimate this local delta invariant. Now we can only also try to use blow-ups in order to do that. So suppose we have a blow-up of this point P, and let E be an exceptional curve for this blow-up. Note that now all the points which maps to point P belong to the -1 curve. So there is a chance that we'll get a good enough estimation using this blow-up curve. So similarly as before, we find this pseudo-effective threshold. Then on the interval from 0 to this pseudo-effective threshold, we find the positive and negative parts of the risky decomposition of the divisor of these divisors. So it's a transform of the initial divisor D and our exceptional curve. Then the log discrepancy for this exceptional curve is 2 because we are now above our initial surface. And similar as before, we compute the S integral. And similar as before, directly from the definition, we get that our local delta invariant is less or equal than 2 over this S integral. Now we want to estimate it from below, and we can, and similar as before, we can compute SW integral, which will equal to the integration of 1 over d squares, where d was our initial divisor. So it's just so we can compute it directly, and this h function is calculated as before. So now we get that our local delta invariant at point P will be greater or equal than these two numbers. So it will be the minimum of 2 over s integral. And here, so remember that before we didn't have an infimum here because it was just one point P. But now we're interested in the infimum for all points O which lie above our point P. So here the divisor E is contains exactly all those points which map to point P. So we need to consider all points O which belong to this divisor. And if we are lucky, our these computations will give us the exact number for local delta invariant. Unfortunately, it's not always the case, but it usually gives good enough estimations. How do we do that? Our example will be easy, so we just take P1 cross P1, and we take any point in P1 cross P1. For any point, we can find a rule in L1 for which this point belongs. Then we can compute the Zariski decomposition. So in this case, this Zariski decomposition is quite obvious. It will be just this divisor from 0 to 2, and the negative part will be 0. Thus, we can compute our S invariant. It will be just 1. So local delta invariant at this point will be less or equal than 1. Then we compute our function h, which we mentioned on this slide. Actually, it's for the curve. We have similar kind of h for the curve, which is on the surface. So we compute our function h and SW integral, which will give us also 1. So in this case, our local delta invariant will be greater or equal than the minimum of 1 and 1, and it will just 1. So in this case, we can see that for all the points on our P1 cross P1, we get that the local delta invariant is just 1. Okay, now that we know how to estimate the local delta invariance, we can go to the topic, to the main topic of my talk. And this is Fano threefolds of the Kähler rank 3 and degree 20. What I want to do is to use this theory for surfaces to help me do the calculations for threefolds. Okay, so how do we build Fano threefolds of the Kähler rank 3 and degree 20? First of all, we take the surface S, which will be P1 cross P1, and consider a smooth curve of degree 5, 1 in this surface S. Now we can have a look at the morphism induced by the projection of S on the first factor from C. Note that the degree of this morphism will be 5, and we can assume that the points 1, 0, 0, 1 and 0, 1, 1, 0 are one of the ramification points for this morphism. Since we can assume it, we can rewrite the curve C. We can assume that the curve C will be given by these coordinates. Note that we can see here that it's the degree, it's 5, 1 degree curve in P1 cross P1. Now we can compute the possibilities for ramification for the ramification index of the first point. It can be 2, 3, 4, or 5, depending on coefficients A and B. Remember that the coefficients A and B were given here. We have here A1, A2, A3, and B1, B2, B3. So depending on A coefficients, we get ramification indexes 2, 3, 4, or 5. Similarly, we can compute ramification indexes for the second point. And we can assume that the first point has the largest ramification index among all points, and the second point has the second largest ramification index for all the points. If both indexes are 5, then all A's and B's are 0, and we have the and we know that the curve C can be rewritten this way. Just substitute A's 0 and B's 0, and the automorphism group of our surface S, which fixes the curve C, will be infinite, and otherwise the automorphism group will be just finite. Now we can consider the embedding of the surface S inside. Remember that we still haven't built our initial threefold X. So we want to do that. We still have a surface and do not have a threefold. Well, now we embed our surface S in P1 cross P2 using the Veronese embedding. So we for the second factor, and then identify our surface S and the curve C with their images in P1 cross P1. And after that, we blow up the identified C in P1 cross P2. And blow up the C, and we denote the structural transform of the S, this S, inside X. Then this X will be a smooth finite threefold in the deformation family number 3.5 in the Morim classification, and every smooth member of this family can be obtained this way. So what we did, we chose, we had this surface S inside P1 cross P2. Inside of S, we had the curve C. Then we blew up the curve C, and we got our threefold X, for which we will try to prove that for some condition this X will be K-stable. What do we know? From the book which I mentioned initially, in which the Kähler problem was posed, we know the following results. So X is K-stable if the coefficients A1, A2, A3, B1, B2, B3 are general enough, where C is our curve. X is K-polystable if all of them are 0, as I mentioned before. And X is not K-polystable if the first three coefficients are 0 and the second three coefficients are not zeros altogether. And we also know that the automorphism group of X is finite if and only if not all of them altogether are equal to 0. And in this case, X is K-polystable if and only if it's K-stable. But how do we prove? What do we want to prove in the end? So first of all, we can consider the projection of this P1 cross P2 on the first factor, and notice that the composition of the blow-up P with this projection gives us the vibration into the Pezzo surfaces of degree 4. Why is that? Because for here we have planes, and the initial curve C was a 5-1 curve. So on each plane we will blow up exactly 5 points. So at the end, this 5 will give us a vibration into the Pezzo surfaces of degree 4, since on each plane we blew up exactly 5 points. And in the conjecture on the book, in the book was that the threefold X is K-stable if and only if the first three coordinates are non-zero. And geometrically, it can be restated that the morphism at which we looked initially doesn't have ramification points of index 5. So we can restate it as follows. Maybe it's an easier way to look at that. So this Fano threefold X is k-stable if and only if every singular fiber of phi have only singular points of types A1, A2, or A3. And the goal of this talk and of my paper was to prove a bit weaker result. So in the first way of saying it, it can be said as the ramification points of epsilon have only ramification points of index 2, then X is k-stable. And in my paper, I proved that if every single, it can be restated as follows. So if every single fiber of phi 1 has only singular points of type A1, then it's k-stable. So remember, the conjecture in the book said that if no matter which kind of singularity we have, A1, A2, or A3, then it's X is k-stable, and I only proved it for A1. But but the proof is very clear. Okay, I guess, I hope. So recall that from the beginning that X is k-stable if and only if the global delta invariant is greater than 1 for all points in X, where delta invariant was defined as follows. So for every divisor above X, we define log discrepancy and S invariant. So basically, we need to show it for all the points, all such points in X. So we start from the point, from any point O in X. We fix it. Now, as we did in the as we mentioned in the first part of the talk, we need to estimate the global delta invariant. And in order to do that, we need to know two numbers. The first one is 1 over S invariant, and the second one is the delta from filtration, where delta should be computed as the infimum of log discrepancies over SW integral for the prime divisors over this surface. So we had a threefold, a surface, and a point on this surface. So since we fixed the points on the threefold, we need to find some surface for which we can compute these two numbers and then apply the theory. Okay, suppose we have this our point O in the surface S tilde which we had initially. Remember, so we had a point, now we have a point O, and we assume that that P1 cross P1, that surface S, in the beginning contains this point. So remember, we had a curve C, and we had a surface S, which is isomorphic to P1 cross P1, and then we blew up this surface C, and S tilde is the strict transform of the surface C, which was isomorphic to P1 cross P1. Since the surface, this tilde C has quite explicit structure, and because it's also just P1 cross P1, the computations for it is quite straightforward. So we just compute first of all S invariant for this surface on that threefold X, Then we rewrite everything in terms of rulings L1 and L2. We can understand explicitly what is the restriction of the tilde s on itself and the anti-canonical, clearly anti-canonical bundle on this tilde s. Then we can just assume that our point S O belongs to one of the rulings, and assuming that on the and that the surface tilde s on the surface y on the previous slide is just tilde s, we can compute pseudo-effective threshold as a risky decomposition, and then we can estimate the local delta invariant similarly as we did before, and the computations will give us that the global delta invariant is just greater than 1. These computations were made in the book for the smooth case, for the whole smooth case. So if you're interested, you can just do it yourselves and then have a look at the computations in the book just to check if your computations are correct. So the computations are quite straightforward for the smooth one. But we are interested in the case where this point does not belong to the strict transform of the surface S, of the surface tilde S. And in this case, we know that for each point we can find a fiber to which of the fibration into del Pezzo surfaces of degree 4 to which this point belongs. So suppose this overline, this T bar is the fiber of phi 1. So this fiber will be del Pezzo surface with at most dual singularities. We can compute the pseudo-effective threshold of the divisor, which is minus kx minus u over line t. So it is a divisor. Then we compute the positive. Then we compute this a risky decomposition, and after that we can compute the S integral. So this is a risky decomposition exists on our threefold X. Then after that we can directly compute the S integral, and then we can try to estimate SW integral, which we mentioned before. It turns out that after all of these computations, we can rewrite it. We can prove using the convexity of volume function. So we have volume inside. We can just say that, okay, since the negative part of the risky decomposition here consists just of S tilde, and we assuming that this point does not belong to S tilde, we can just get rid of the first part of our integral and concentrate on the second one. Then we can split it into two integrals, and then since the volume is a convex function, we can get rid of this thing and notice that now we just that this thing will be less or equal than two similar integrals, and after rewriting it in a bit, we can say that it's less or equal than 6/5 over log times log discrepancy over a local delta invariant for the del Pezzo surface, which will give us that if the local delta invariant for the del Pezzo surface T bar is greater than 6/5, then the global delta invariant of the threefolds is greater than 1. and we are basically done. So if we give all the computations only for curves for which local delta invariant is less or equal than 6/5, and the result will be proven for them. And then for all the others, we will have automatically that the global delta invariant is greater than 1. And note that we know I calculated all local delta invariants, at least estimations for them, for Duval-Del-Pezzo surfaces of degree 4. So for smooth delta invariant of Del-Pezzo surface of degree 4, all the points it is true for all the points that the local delta invariance is greater or equal than 6/5. That's why if all the fibers are smooth, the result directly follows from this point, because local delta invariance is greater or equal than 6/5. So global delta invariant is greater than 1, and we get our result. For a one singularity, we only need to check these two places. So we only need to check, it's the dual graph of negative curves on this surface. Now we only need to check the middle one. It's the weak resolution of the Duval-Del-Pezzo surface and the lines around it. And they are almost symmetric. So instead of doing the computations for the general point, we only need to do the computations for the middle curve and the curves around it. And it reduces the generality of computations dramatically. For y plus 1, we here we will only need to check the curves which belongs to this point. So basically it's this curve, and the curves around them. And they all also have some kind of symmetry. So the number of computations reduced dramatically. When we go further, this case actually does not appear, but we can only also see that we don't need to choose a general point. We only need to check negative curves, and so on and so on. Note that in A2 we will need to check more curves, because the worse the singularity, the lower the numbers. So for the case A2, we will need to check these two, basically all the negative curves, but I will talk later about it. And there are also several other possibilities. So we have only A singularities, but that can be at most A4, hypothetically, but not in the reality, but hypothetically you can. So what is our proof? We see that if the Duval-Del-Pezzo surface T bar is smooth, then, as I mentioned before, the local delta invariant is greater than 6/5. So the global delta invariant will be greater than 1 directly. Now we assume that the point O does not belong to tilde S, and our Duval-Del-Pezzo surface is singular. Similar as before, we define a local delta invariant for this point. Then we compute the log discrepancy for any divisor f over this Duval-Del-Pezzo surface, and the S invariant. And we will prove that there shouldn't be this a second overline T here. I will correct it in later notes. So we will prove that local delta invariant for this pair is greater than this function for every point u inside the interval 1, 2. And after we prove it, we can rewrite it as W integral just as sum of these two integrals, and then using that this local delta invariant is greater or equal than this function, we can rewrite. We can say that the sum of these two integrals would just be less or equal than the sum of this integral and this thing. So the estimations for the second integral are just as the ones which we had for the previous estimation. So it will be just one of those integrals on one of the previous slides. And for this integral, we can rewrite it as this is the volume of the divisor D, and here will be our local delta invariant. So since our local delta invariant for this pair will be greater or equal than this function, then the first integral will be less or equal than the volume of the divisor D over this function. And after integrating, we'll have that this SW integral will be less or equal than 99 over 100 log discrepancy of the any prime divisor f over tilde s. So since we know it for the arbitrary prime divisor f over our Duval-Pezzo surface, then the infimum of these guys will be greater equal than 100 over 99 for all prime divisors f over our Duval-Pezzo surface, so that local delta invariant will be greater or equal than 100 over 99, and which is greater than 1, and then x will be K-stable. But how do we prove it? So suppose our Duval-Pezzo surface T. Suppose we have our Duval-Pezzo surface over line T. Then we can look at the resolution of the singularity on this Duval-Pezzo surface. And actually just a blow up. It's not a weighted blow up. It can be just written just as the blow up. For the point, for the u inside the interval 1, 2, our polarization can be seen as this, where C2 is just the restriction of our surface S on the Duval-Pezzo surface over line T. This C bar is contained in smooth locus of the surface T bar, so we can just look at its strict transform, and it will be no any unexpected exceptional divisors in there. Then we can rewrite our polarization as D, which will be minus KT minus 1 minus U C2. Why C2? Because C2 is is in fact a conic, because after that initial embedding of the curve C inside it was a 5-1 degree curve, and then we embedded it using the nature of embedding. It was of degree 2 on the second factor, so now it became a conic. So after that, we can rewrite our divisor D and get a new polarization of the pair, and we can also compute its volume for any point u for any value of u inside of the interval 1, 2. Similarly as before, we define a local delta invariant first on t bar and then on t. So t bar is the volatile Pezzo surface below, and t is the weak Pezzo surface above, which maps which resolves the singularity on t bar. And we can see that the infimum of the local delta invariance on 4 points which map to the point P will give us the local delta invariant on the t bar. Remember that to estimate local delta invariant on the surface, we first need to choose on the point. We first need to choose a point, a curve which passes through this point. Then the compute this Zariski decomposition. Then compute S invariant and log discrepancy. Well, if it's a curve on the surface, it's just one. And then we get the estimation from above. Using Apanjan theory, we get the estimation from below, and then if we're lucky enough, we get we get our result. If not, not. Let's see how it works, for example, for one singular point of A1. So we have, we get it as the blow up of P2 at 4 points. And after that, we know the how the graph, how the dual graph of negative curves looks like. Remember that we only need to check the middle curve and the curves around it. I will only show the computations for the middle curve, because usually the worst numbers are, and the least numbers are for the -2 curves, or like if we have several -2 curves, is this central -2 curve. So suppose we have a point which belongs to this middle curve, then as before we compute positive and negative part of the Zariski decomposition, then we compute the volume for each part of the where the Zariski decomposition changes. Then we compute the intersection of this volume with E4, which we will need to compute the SW integral. After we compute the S integral and get the estimation from above, so here we see that it's some function which from U. So it's for different U's, we have different numbers, basically. And similarly as before, we compute the H function for each point of this divisor E4. And after that, we can see that for the points, here we have three options, because for different because E4 it intersects with some curves, so depending on the configuration of intersection, we will get different function. But after we choose a minimum for each interval, we can see that the local delta for this pair will be greater or equal than this function for any point. So we can see how this that delta will be greater or equal than some function from U on interval on where U belongs to interval 1 to 2. That's basically how we can prove the result for points of type for the case where all the singular points of our vibration is just A1s. And for A2, for the singularity of type A2, this estimation will be not good enough. So some different approach should be chosen in order to in order to prove the result. So thank you for your attention. That's it. Thank you.